Hey folks, let's finish up these 2.3 product and quotient rule notes. So we've already talked about the derivative of sine and cosine. Now we're going to add the other, the big six to the mix here. We're going to add tangent, secant, cotangent, and cosecant. So like I said, we've already done d dx of sine is cosine, and then d dx of cosine is negative sine. Yes, this is something I expect you to memorize. These six I expect you to memorize. Those who plan on taking the AP test, you'll have some more to memorize. So let me give you some hints. Look, first of all, at how close they are to each other. So we've got sine goes with cosine and back and forth. Now tangent is matched up with secant squared, but look at cotangent. Tangent is with secant, so cotangent is with cosecant. Secant starts with secant and flips to tangent. Cosecant starts with cosecant and flips to cotangent. So what I did as a student, I memorized these, and then I just worked from these to know these. Now notice, this is cosine, this is cotangent, this is cosecant, and all of those cos, when you derive them, will have a negative out in front. So however you memorize them, that's up to you. That's your call. But I do expect you to memorize these. All right, so let's find the derivative of each of the following using your memory. Actually, these are kind of nice to prove. If you look back, we already proved one of these. What do you notice that sine over cosine is the same as? Sine over cosine is the same as tangent. When we derived it, look what we got, secant squared. And if you'll notice, what's the derivative of tangent? Secant squared. So if you do forget these, you could always just prove them again using the quotient theorem, but I would recommend just learning them by memory. Okay, so first of all, what type of problem is this? This is overall a difference. So I first decide what type of function I have. It's a difference, so I can derive this, I can derive this. Those are both nice to derive, so I don't have to do anything fancy. I would get g prime of x is equal, what's the derivative of x? 1. We just learned what's the derivative of tangent is secant squared, so I would get negative secant squared. All right, now from here, you can actually clean this up a little bit more. College Board expects you to know all of the Pythagorean identities. I don't expect you to know them all, but I expect you to know the big one. And what's the big Pythagorean identity? The big Pythagorean identity is sine squared plus cosine squared equals 1. That's the big one. And then to find the other ones, what we can do is we can take this and divide by either sine or divide by cosine. Because I want secant, what should I divide 1 by to turn it into secant? Well, secant's the reciprocal of cosine, so I'm going to take this and I'm going to divide everything by. This is me showing you how to do this if you don't remember the trig identities by heart. So I want secant, so divide by cosine. So I'm going to divide each piece of this by cosine squared. Cosine squared x, cosine squared x, cosine squared x. And what I get, what's sine over cosine? Tangent. So what's sine squared over cosine squared? Tangent squared. What's cosine squared over cosine squared? 1. And what's 1 over cosine squared? Secant squared. Now, you might remember that from when we did those trig proofs last year in pre-calculus. Okay, so the problem here is I want this to look more like this. So I'm going to move this 1 to the other side. So therefore, tangent squared of x is equal to secant squared minus 1. So look at what we have now. And look, I know this is a lot. This is more of what I would expect out of College Board, not out of my tests. College Board expects you to be able to recognize these identities. So that's why I'm going through how to find this again. So this last part, though, I would expect you to be able to do. I want secant squared minus 1 because I can sub that in. The problem is I've got it backwards. So what does it cost to take something with a subtract and flip it around? I hope you remember that it costs a negative. I would take out a negative. So g prime of x is equal to negative tangent squared of x. Okay, let me just do a quick review why that's true. Secant squared minus 1 is the same as tangent. I have a positive 1 and a negative secant. So if I make this negative and I make this positive, if I times this whole equation by negative 1, I would have a positive 1, I would have a negative secant, and I would have a negative tangent, which I can then sub for. All right, let's try the next one. Like I said, that's more of a College Board type problem. That's more than what I expect you guys to be able to do. The next one I very much expect you to be able to do. This to me would be an easy problem. So overall, what type of rule is this? X secant x. Overall, this is a product rule. If this is a product rule, then I need to identify my u's and my v's. My u is x. Derivative of x is 1. My v is secant. Derivative of secant, if you don't have it memorized, secant starts with secant. That's how I memorized it. And it switches to tangent. Alrighty. This is a product rule, so I'm doing u prime v plus uv prime. So y prime would be equal to 1 times secant, which is just secant, plus x times secant x tangent x. And I don't know, I would probably leave it like this. Maybe you could factor out a secant. So y prime is equal to secant of x times the quantity 1 plus x tangent of x, which I'm not so sure that that's any nicer. I would have left it like this. I would have left it like that. But who knows, on a multiple choice, I can guarantee this would not be a free response question. I can guarantee if you'd see this question, it would be a free response question. So they maybe would leave their answer like this. Maybe they would leave their answer like this. You've got to be flexible with your algebra to be able to go back and forth. All right, differentiate each of the following, then show how they have equivalent derivatives. So they're saying that these two things are actually have the same derivatives. Well, let's go ahead and derive this. So you pause it. We've had enough practice. Pause it and derive this. Okay, overall, this is a quotient rule. Now, technically, it's a quotient with a sum, but I don't talk about the sum or difference rules unless it's the overall rule. So this is a quotient rule. My numerator, my u, is cosine 1 minus cosine. U prime, the derivative of 1 is 0. All right, the derivative of co is going to be negative. So there's already a negative. It's going to be a negative, which is going to turn out to be a positive sine of x. My v is sine of x. The derivative of sine of x is cosine of x. This is the quotient rule. So u prime v minus uv prime. So I'm subtracting. All right, so f prime of x is equal to u prime v. So that'd be sine times sine. Well, sine times sine is sine squared. Minus u times v. Now I'm going to put I always like to put the term that has only one piece to it first. You don't have to do it that way. But I'm going to put the cosine first. And then the chunk that has more than one piece second. All over, don't forget this part, all over v squared. So that would be sine squared. Now, I would expect you to try to clean this up to see if there's anything we can do to make it look a little nicer. My math voice says to distribute, so I'm going to distribute that negative cosine. So I get sine squared of x minus cosine of x. A negative times a negative is a positive. Cosine times cosine is cosine squared, all over sine squared. First of all, can I kill off those sine squareds? No, you cannot, because there's not a sine squared in every piece. And can I kill off the squared? No, because add and subtract messes up exponents. But I do expect you to see a move here. I do expect you to see a move. What do you notice? Do you see anything on the top that can be cleaned up? This is the Pythagorean identity I expect you to see. Do you see it? Do you see it? Sine squared with a cosine squared. Sine squared plus cosine squared equals 1. So I can rewrite this now as sine squared plus cosine squared is 1 minus cosine all over sine squared. And I would expect you to clean this up a little bit more. We can make this look a little bit fancier. Actually, yeah, no, I would expect you to clean this up. So what I can do here is, we've talked about this already. What do we do with a fraction that's one fraction and we want to make it into two fractions? I can take this and I can split it up. I can split this into 1 over sine squared minus cosine over sine squared. Now, this is all that stuff that we did last year with the trig identities and the trig proofs. That's what's supposed to be coming into your mind at this point. So your math voice should be yelling at you something here. What's 1 over sine squared? Hopefully it's yelling cosecant squared. Minus. Now this is a little bit creative. I would argue that it's worth it. It's okay if you didn't remember this one. I might need to give you a little reminder. So what I can do in this scenario, this was like one of the last examples of our trig proofs last year, is I can take this and I can break it apart. I can split this up into 1 over sine times cosine over sine. And you might say, how would I ever know to do that? Yeah, I agree. I get it. But now that you've seen it, maybe you'll remember it a little bit more next time. And maybe it's not as confusing as when you saw it the first time we did this last year in pre-calculus. But anyway, I can now rewrite this. 1 over sine is cosecant times cosine over sine is cotangent. Now, I could factor out a cosecant here, but it would leave me with a cosecant minus cotangent, which isn't any better. So there we go. All right, now we're supposed to differentiate the next function. So now we're supposed to derive g. So this is nice. Overall, what type of rule is this? This is a difference rule, which means I can just derive each piece. G prime of x. What's the derivative of cosecant? Okay, first of all, it's going to be negative. Cosecant starts cosecant and switches to cotangent. Then minus, what's the derivative of cotangent? Well, it's going to be negative, so that's going to change that back to a positive. And then cotangent is, so tangent is secant, so cotangent is cosecant squared. If you don't have that memorized, memorize them. Now, if I do a little rearranging here, I get that g prime of x is equal to cosecant of squared of x minus cosecant of x cotangent of x. Okay, so what's the point of all this? The point of this example, the idea here is Corpy's trying to show you, if you simplify early and often, you can save yourself some headaches. Would you rather have derived this, or would you rather have derived this? Obviously, we would rather not do this. This took way too long. Plus, we had to remember some Pythagorean identity that we might not have remembered. This takes forever. And then we had to clean up at the end again. So to avoid that, if you can clean up early and often, do it. So I'm going to take now, instead of doing a quotient rule, I'm going to take this thing. How do I want to box this? I'm going to take this and I'm going to clean it up first. And you can do this a lot with trig functions. Clean up first. So my math voice says this is f of x equals. My math voice says I've got a fraction that's over one thing, so I can split it up. So this becomes 1 over sine minus cosine over sine, which equals, what's 1 over sine? Cosecant minus cosine over is cotangent. Look at, we could have done just this, but the cost for doing that is that you have to clean up first. So keep your eyes peeled. Once we do that cleanup, now we don't need the quotient rule. Yay, smiley face. If I can avoid the quotient rule, I can. Simplify early and often. Simplify early and often. Well, you might say, how would I have thought to do that? I get it. You wouldn't have. That's why I showed you. So now maybe you can take my advice the same way I learned about it when somebody showed me how to do it, and then I tried to remember it from there. All right, some other things that we want to try to memorize. If you haven't done this in physics yet, I assume it's coming at some point. This is the relationship between position. If you take the derivative of position, it gives you the velocity. If you take the second derivative of position, it gives you the derivative of velocity, which gives you the acceleration. So position. Now they use S, they could also use X, they could also use H. Those are all measurements of kind of like how high the graph is. Then we have velocity. Velocity is equal to the derivative of position. That gives us the velocity function. And then we have this function called acceleration. The acceleration function is the derivative of the velocity function, which is the derivative of the second derivative, the derivative of the position function. This is worth memorizing. What would be a good color here? Maybe purple. Memorize. This is worth memorizing. I can almost guarantee that there will be, probably not a free response, it'd probably be a multiple choice, but I can almost guarantee that there would be a multiple choice question involving some sort of projectile motion where you have a position, you have a velocity, and you have an acceleration. Now, we already talked a little bit about this. These are multiple derivatives. So we call the first derivative y prime or f prime or dy dx or d dx of f of x. But we could also take the derivative of that derivative, and then the derivative of that derivative, and the derivative of that derivative, and on and on and on and on. So after the fourth tick mark, you can either just write after the third tick mark, you can just go to the number 4. I actually still go with Roman numerals, but it doesn't matter, however you want to do it. All right, so let's do a couple where we go more than just one derivative. So if y equals blah, 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 find the y to the 5th of x. That means the 5th derivative of x. So, actually, you do this. Do this on your own while I do it. It's so nice because we can do the derivative shortcut. I'm going to take the second derivative, take the third derivative, I take the fourth derivative, I take the fifth derivative. That's the one that they wanted. All right, so let's go over here now. What? They want to take the 58th derivative? They want us to do this 58 times? Whoa. Let's see if we can avoid that with trying to figure out a pattern over here. This was x. What was the degree of this function? Remember, the degree is the highest exponent once everything's distributed. So the highest exponent once everything was distributed was a 3. How long did it take before we got a derivative that was 0? It looked like it took 4. Let's do a test. I'm going to make up a real easy equation, and we're going to test it to see if we can save ourselves some headaches here. I'm going to make this y equals x squared. Okay, what's the first derivative? 2x. What's the second derivative? 2. What's the third derivative? 0. What's the trick? So how many derivatives do you have to go before it turns into 0? You have to go one more than your degree. So this was a degree 2, so I had to go to the third derivative to get it down to 0. So this is a really easy problem. Let's just make sure 57 is our degree. Yep, there's no exponent higher than that. So if you want me to derive 58 times, the game is over. F, the 58th of x would end up being 0. Now these next two, I don't know if these are one of those that just because I'm making the video, I'll show them to you. If there was like 10 minutes left in class, I'd show them. I don't remember seeing this a lot. So this wants us to take the 447th derivative of sine. Well, what's interesting about these and what makes this kind of a fun problem is what's the derivative of sine? Cosine. What's the derivative of cosine? Yeah, hold on. So I don't remember where I left off, but the idea here is that you've got sine's derivative is cosine. Cosine's derivative is kind of a sine thing, which then would flip back to sine, cosine, and then sine, and then cosine. So that's the idea. So what we're going to do is we're going to look first at what are some of the derivatives of sine. So what's d dx of sine of x? Derivative of sine is cosine. What's the second derivative? And that's written d squared with a dx squared of sine of x. So what that means, I'm going to take the derivative that I got before and derive it again. So what's the derivative of cosine? Is negative sine. And then I take the derivative again, so that would be the third derivative. So that's d cubed over dx cubed of sine. Okay, so that's the derivative. The derivatives, derivative. So what's the derivative of sine? Is cosine, but there's a negative out in front, so that would be negative cosine. The fourth derivative of sine, what's the derivative of cosine? Negative sine, so there's already a negative and a negative make a positive, and we get back to sine. So then what's the derivative of that? Well, then it would just go back into this pattern again. The fifth derivative would be the same as the first derivative, the sixth the same as the second, the seventh the same, and so on and so on and so on. Therefore, we have a pattern that repeats after the fourth derivative. So if I wanted to figure out the 447th derivative, I would have to see how many times groups of 4 fit into it and what that remainder is. So I'm going to take 447. Like I said, I don't remember you guys ever seeing this. I'm sorry, I don't remember ever seeing this, but it's kind of interesting, I guess, to show. But I don't think you'll really need this. If you're like, how would I remember to do this? This is one that I wouldn't expect you to spend a ton of time on. Okay, so I'm going to take 447. I'm going to divide it by 4. Okay, so 4 goes into there once. 1 times 4 is 4. Remember the saying, draw the line, switch the sign. 4 minus 4 is 0, so this 4 drops. 4 goes into 4 once. 1 times 4 is 4. Draw the line, switch the sign, so that's 0, so the 7 drops. 4 goes into 7 once. 1 times 4 is 4. Draw the line, switch the sign, so I have a remainder of 3. So I can now say, therefore, the derivative of 447, the 447th derivative of sine is exactly the same as the third derivative of sine, which is, what's the third derivative of sine? Negative cosine. I wonder if you could try the next one on your own. Pause it and try the next one on your own. See how the pattern works for cosine. Okay, let's see how you did. So first of all, I got to figure out what are the derivatives of cosine. So d dx of cosine of x is negative sine. The second derivative of cosine is, derivative of sine is cosine, but there's a negative, so that's negative cosine. The third derivative would be the derivative of this, which would be a negative, negative, and then a sine. And now I'm hoping that the fourth derivative takes me back to cosine, which it looks like it will. So that'd be the derivative of sine, which is cosine. Okay, so this is the same thing. Pattern repeats. After fourth derivative. Okay, so let's go ahead and figure out, oh my gosh, Corpy, you're killing me. We now have to take this and divide it by 4. I would encourage you to try to do this on your own. I know it's a lot easier when you watch me do it, but it doesn't give you any good practice. All right, so what do we have here? 8, 6, 7, 5, 3, 0, 9. Divided by 4. If you haven't done this yet, pause and try to do it on your own. 4 goes into 8 twice. That makes an 8. Draw the line, switch the sign. The 6 drops. 4 goes into 6 once. 1 times 4 is 4. Draw the line, switch the sign. The 7 drops, so that would be 27. 4 goes into 27 6 times. That's 24. Draw the line, switch the sign. That's 3. And then the 5 drops. That's 35. That goes into there 8 times. That's 32. Draw the line, switch the signs. That's 3. The 3 drops. 4 goes into 33 8 times again. That's 32. Draw the line, switch the sign. That's a 1. I'm running out of room. That's a 0. 4 goes into 10 twice. That's an 8. Draw the line, switch the sign. That's a 2. The 9 drops. 4 goes into 29 7 times. That's 28 with the remainder of 1. So the derivative, I guess I'll write it in green. Therefore, the, oh boy, what number is that? 8 millionth, 675th, 3004, 3009th derivative of cosine is exactly the same as the first derivative of cosine. And the first derivative of cosine is negative sine. Like I said, not a hugely important example, but kind of an interesting one. All right, I love these. These are my favorite thing. All right, so we've got a table. This is what we call sparse information. You're not given a ton of information, but we're going to use that table to help us figure out these derivatives. So the table above gives us specific values for two differentiable functions and their derivatives at selected values. We're going to use the table to evaluate this. So I want to evaluate what is the derivative of h at 0. Well, h of x equals f of x over g of x. What type of rule is this? This is a quotient rule. Okay, so if I'm going to do a quotient rule, that means I need u's and v's. U is equal to f of x. Now this gets interesting. U prime is the derivative of f. Well, we don't know what f is, but we do have a name for its derivative. Its derivative's name is f prime. V is equal to g of x. Its derivative's name is g prime of x. Now we are doing the quotient rule. So that's u prime v minus uv prime. So h prime of x is equal to u prime v, which would be f prime of x, g of x, minus uv prime, which would be f of x, g prime of x, all over g squared of x. Now, that's the derivative function for x. We now want to figure out what's happening at specifically 0. So now I'm going to plug in 0 for all these things. So that would be, let's change colors here. That will go back to the blue. So that would be h prime of 0 would equal to f prime of 0, g of 0, minus f of 0, g prime of 0, over g squared of 0. Now, these are all things that I can figure out from my table. F prime of 0. I go to f prime, I go to 0, I plug in negative 3. Times g of 0. I go to g, I go to 0, I get 5. Then we got f of 0. F of 0 is 2. Minus 2 times g prime of 0. G prime, go to the 0 column, would be negative 1. Over g of 0, which is 5 squared. Now we can start to clean this thing up. Negative 3 times 5 is negative 15. Negative 2 times negative 1 is positive 2. 5 squared is 25. That would end up being negative 13 over 25. So even though they didn't tell me all the data points for f and g, and f prime and g prime, I can use that to figure out enough to help me find specifically at the point 8. Now, if they asked me to find h prime of 2, I'd be in trouble because they didn't give me any x values at 2. So we would say we couldn't, not enough information. Okay, let's see how you do at the next one. First of all, decide what type of rule is it. So this is overall, this is a product rule with products in it. So this is what product with a product. Product with product. Because I've got these two things multiplied together, and then that's multiplied by this. So when I set up my u's and v's, I'm going to have two different setups. So let's start off with my first product. And it doesn't really matter what you choose as your products. I'm going to choose u to be x times f of x. U prime is equal to v then would be equal to g of x. Now v prime is really easy to figure out. That's just g prime of x. But now I chose to put the product here and then times it by that. You could go in the other direction. You're going to get the same answer. But when I try to derive u, I've got another product. So that means I need to make another table for the product rule of that piece. So that would be product again. But this time my u is x, u prime, and my v is f of x. Okay, so what's the derivative of x? 1. What's the derivative of f of x? F prime of x. Now I'm going to take this product and I'm going to put its answer back up here into u prime. So that's u prime v, which would be f of x, plus uv prime. So that would be x f prime of x. So I use this to get this product rule. I had to make a product rule table. And now that I've got that product rule in here, I can now use this whole table to give me the actual derivative that I'm looking for. So that would be h prime of x would be equal to u prime v. So I'm going to use parentheses here. F of x, there's no way I'm going to have enough room for this. F of x plus x f prime of x times g of x plus, and then I'm going to run out of room here, so I'm going to go down here, plus x times f of x times g prime of x. So I took my u prime, I multiplied it by my v, plus I took my u, multiplied it by my v prime. Okay, so now this time I'm not going to show as much work here. I'm just going to kind of plug and chug. So what would be a good color to finish up here? Let's go with, we haven't used orange in a while. So going from pink to orange isn't very fun. Let's go with a kind of this weird red. No, because that kind of goes just the same. How about a brown? There we go. H prime of -1. Now this time I'm just gonna start plugging and chugging. So I need f of -1, which would be 3, plus what's x? -1 times, my gosh, I'm not gonna have enough room again. F prime at -1 is 4 times g at -1, which is -2, plus, oh boy, can I squeeze it all together? X, which is -1, times f at -1, which is 3, and then g prime at -1, which is -2. And let's see how this works. Okay, so this is going to end up being 3 plus -4 times -2 plus 6. I screwed this up. That's -1. Dang it, where did I screw this up? X is -1. F of -1 is 3. G prime, I took G, it's G prime is +2. So that's going to make this a -6. Sorry about that. So this ends up being -1 times -2 minus 6. Negative times a negative is a positive. 2 minus 6 ends up being -4. And I've got a nice warm-up that I plan on doing that'll practice that for us. Okay, last little bit here. This one's fairly quick. Okay, we've got this story. The position function for a falling object on or near the surface of the moon is given by this equation. So this is the height equation. Where you drop something on the moon from the height of h0, where h of t is the height and h of 0 is the initial height. So if I'm at 30 feet in the air and I start dropping a bowling ball, it will fall at this rate. Height will be calculated by this. So if you're eating at an Italian restaurant on the moon and your meatball rolled off the 3.2 foot high table, what does that mean the 3.2 is? 3.2 foot. 3.2 feet high table. This is my initial height. Initial height. In other words, h of 0 equals 3.2. That's what that's telling me. So I can now plug that into my formula. After how many seconds would it hit the floor? Okay, so what's our equation? Let's do that first. H of t is equal to negative 2.66 t squared plus 3.2. That puts us at a height of 3.2. Now what we want to see is after how many seconds would it hit the floor? Well, when does the meatball hit the floor? At what height does the meatball hit the floor? The meatball hits the floor when h of t, the height, is equal to what? Well, if you're on the floor, you're at a height of 0. So what I want to do is I want to take my height equation and I want to set it equal to 0. So I would say negative 2 point, so negative 2.66 t squared plus 3.2 equals our height of 0. All right, let's use a little algebra here. I'm going to subtract over, so I would get negative 2.66 t squared equals negative 3.2. Divide both sides. T squared equals negative 3.2 over negative 2.66. This is not something that, it didn't say on here that we could use our calculator. They would never expect you to do this, something that crazy by hand. So we can use our calc here. All right, so I'm going to show you a trick. So I'm going to do negative 3.2 divided by negative 2.66. We get this crazy decimal. So I get that t is equal to plus or minus 1.203. Remember, we truncate in AP Calculus, which means after the third decimal point, you just chop it off. Now, I know one of those won't make any sense, but because it's negative. So that's not part of our answer. But what I want to do here is I now want to store as A. What that means is we don't have to use, we're going to need to use this number later on, or if we need to use this number later on. What we can do is we can store this now. If you hit the STO button down here at the bottom, hit store, and then choose alpha A and hit enter. That means whenever you type in A, it will give you that number again. So if I wanted to do 3 times A, it's 3 times 1.2, which is like 3.6. So it saves it as that number. You guys maybe did this in chemistry class where you store Avogadro's number in your calculator. That's what this does, store. Okay, well, let's answer the question here. The question was, after how many seconds would it hit the floor? So the meatball, we'll do a little write-up. The meatball hits the floor at time t equals 1.203. And does the story have units? Yes. So you've got to put units in there. Where am I getting negative 3.2 divided by negative 2.66? Huh, my other notes were, oh, I forgot to square root that. God darn it. Dang it. Man, I'm rushing here to try to get these notes done. Okay, sorry guys. This was still t squared. So I'm going to cross this out. So let's try this again. Negative 3.2 divided by negative 2.66. And then I need to square root that. So second square root, second answer. That's better. So now I get that t is equal to plus or minus 1.096. No, we don't round that. We truncate it. 1.096. Now I want to store that as A. Now A is now that number, so when we use it later on. So let's actually answer the question properly this time. The meatball hits the floor at a time t equals 1.096 seconds. Notice I wrote the word time in front of my variable, and then I put units after that time. Okay, so there was a second question. It says, how fast was the meatball traveling when it hit the ground? So that means I want to know its velocity. I want to know the velocity at the second that it hit the ground. Well, what do we know about velocity? Well, if you haven't memorized it yet, that's fine, but you want to get to a spot. It turns out that velocity is the derivative of position or the derivative of height, depending on how you say it. So if I take my height equation and I derive it, I would take this, I'd multiply it by 2. So negative 2.66, I got to do this on my calc, I can't do that in my head, is negative 5.32. Negative 5.32, and I subtract 1 from the exponent. That's a constant, so hey, that's it. There's my equation. Now what we want to do is we want to figure out the velocity at the moment it hit the floor, and it hit the floor at this number. And luckily, so that means I want to figure out what is velocity at 1.096. Well, what's nice is we don't have to round this number. We stored that number as A. So I'm now going to type in negative 5.32 times alpha A, and we get negative 5.835. Okay, so let's do a nice little write-up on this so it looks nice and neat and organized. So we'd say something like the meatball hits the floor at a velocity of negative 5.835, and then you got to put units on this. This is velocity is feet per second. Using the given equation, determine how many times stronger the acceleration due to gravity on Earth is compared to that on the moon. Well, let's review acceleration due to gravity on Earth. And you guys might remember this from physics as well. The gravity on Earth is equal to negative 9.8 meters per second squared, or in another form, negative 32 feet per second squared. So depending on your units, you'll get a different number there. So for us, in this story, we're talking about feet per second, so we want to use this number of negative 32. What's the acceleration? Acceleration due to gravity on the moon. Okay, so we've got to figure this out, but what do we know about acceleration? Acceleration is equal to the derivative of velocity, which is equal to the second derivative of height. So we've already derived the velocity equation and got this. So if we derive it again, that coefficient, or that 1 is going to get multiplied. It's just going to be negative 5.32. So the gravity on the moon is equal to negative 5.3 feet per second squared, which makes sense because the moon is a smaller object, so it would have a smaller gravity. So if we wanted to compare how many times stronger is the gravity on the Earth versus the moon, so I would need to then take the gravity of the Earth and divide it by the gravity on the gravity on the moon. Gravity on the Earth is negative 32. Gravity on the moon is negative 5.32, which, what do we get when we do negative 32 divided by negative 5.32? We get about 6.015. So we could say now that the gravity on Earth is 6.015 times stronger than on the moon. So based on your answer to part B, determine what your weight on the moon would be. Well, let's just assume, I don't think anybody wants to talk about their weight. Maybe you do, I do not. Let's just pretend like my weight is a nice 150 pounds. Right? Right. Obviously. I'm going to put a little obviously underneath there. My weight is obviously 150 pounds. Ignore my belly. Anyway, so if I wanted to figure out how much I would weigh on the moon, I would take 150 pounds and I would divide it by the factor of how much we weigh on, how much stronger it is on the Earth, which ends up being 150 divided by 6.015. Hey, dude, diet problem solved. I would only weigh 24.937 pounds. I don't think I want to weigh that light on the moon. Okay, so there we go. That should be it for our notes for 2.3. Give that homework a try and ask me some questions in class if we need to.